Probably.
Yeah, same line.
There are no stupid questions.
So stupid answers.
Wait, hold on.
Yeah.
AJ, go ahead. Well, let's hear yours first.
You were talking about how
Guys, listen up.
when there is when it takes the air out of the O2 when there's fuel. Does that?
I'm smiling because I'm still confused too on this subject.
I just want to like. Does that cause like the O2 to fail if that happens over time?
if what happens? I'm sorry.
If you know how like there's the exhaust gas flowing by the needle or whatever you want to call it, and then there's still the atmospheric inside.
Yes.
And when it pulls that out,
yes.
does that air like ever run out, or does it fail because of that?
Technically, from what I've read, because the O2 is a catalyst, it never goes back.
Okay.
It actually becomes contaminated.
Okay.
And O2s get
Is
contaminated.
that why it would go bad?
That's why they quote go back.
The engine code would kick in.
Yeah, well, contaminations can occur from a lot of things. One can be from an external, where it's a great question, by the way.
I guess like the corrosion end.
You can get external crap in here, like if you were spraying brake clean carelessly around your O2 and you've got brake cleaner down inside that. Yeah, are you done with the lollipop thing? Sorry, good. That's okay.
He wasn't here yesterday.
It's fine. No, but this desktop recorder, it picks everything up. Damn. Hold on a second.
Hi guys.
What are you doing, man? How you feeling?
Oh, rain every day.
Yeah, but you're
recording.
Yeah, it is.
Sure.
All right, sorry for that little distraction there. Great question, AJ. If we get contaminants in here, we can have an issue. If we get contaminants out here, we'll have issues, say, coolant. If you're burning coolant, if you're burning engine oil, if your mixture's skewed for a long period of time, you ever pull a spark plug out and see all that black soot that's on a spark plug? That same crap's going to end up on that O2. All of that's going to interfere, I think, with this catalyst process that's taking place on this. I want to learn your name, so Dawn, you had a question.
My truck has been like screwed up for the past like 8 months. I have a wire. I don't know if it's a wiring issue. I don't know if it's a starter. You start the truck up and it runs. Like you had to put a battery charger on it. It will start up.
Okay.
Put a new starter, alternator, battery.
So this is completely unrelated to what we're talking
about.
Right?
Well, it was from yesterday when you were bringing up wires. That's why I said it was from yesterday.
All right. I'll give you that.
And
I was about to stop you.
Yeah, but no, and I'll shut it off and it'll just do nothing.
What kind of truck?
S10.
What do you mean do nothing?
Like if you just turn the key, it'll just stay blank. Like nothing will move.
No sound of the starter or anything.
Nothing.
Not even the fuel pump take on?
Sounds like a loose nut behind the wheel.
You should hear his horn.
You'd be the loose nut behind the wheel.
No, I mean.
I'm sorry. If it's not cranking, it's a starting system problem. Anti-theft, ignition tumblers are common on that. It's something we can look at, but yeah.
Yeah, I have no idea. Yeah,
we can handle. When we go to shop, we'll get that in. We'll take care of it.
How are you gonna get it here?
I need my cheat sheet.
Scott,
Scott has a question. Go ahead, Scott.
So my grandma.
Guys, listen up.
My grandma's van.
Is this related?
Yes.
Okay, good.
She had a misfire, and we found out like there was she was losing coolant. We found out it was the head gasket.
Yes.
And the coolant was going through the system.
Yes.
Would you suggest replacing the O2
all of them.
sensors then?
I would include it. I wouldn't say that it's needed. I think it would be wrong. It would be wrong to say to a customer, you have to change all of your oxygen sensors, but you need to let those people know that the contaminants are a real possibility, and they're really, you may not know until you're done with the job, and you might want to make sure that they're aware of that. Yes, AJ.
Would you at least suggest to do the like upstream?
I think it would depend on the cost of the upstream O2.
Okay.
Yeah, it would really. Some of these European cars, you might spend $200-300 on an oxygen sensor, and I'm certainly not going to want to change that just because I think it might need it. I think I would.
Well, you would let them know,
absolutely,
suggest it, and if they do come back, then you say, yeah.
Yep, exactly. Half of the battle here, guys, is communication with your customers. As long as they're aware of the potential, they're not going to be angry with you when they're done. You know, they might be angry if they spend $1,500 to $2,000 to say do some cylinder head gaskets, and you're done, and now you tell them they need even if it's a few $100s more, they're not going to be happy with you. So yeah, absolutely, these are things we need to think about. Now, Jorge, did I say that right?
Yes.
All right, that's an unusual name for me. I apologize. Jorge and I were talking briefly when you guys went to break, and I think I maybe have a little bit better understanding or explanation for this last part, and I want to see if this makes sense. All right, here's what we know. That this being outside oxygen and this being my exhaust gases is what we've been using. It is the transfer of these oxygen ions in some way, shape, or form that cause the O2 to make voltage. It's not the imbalance of oxygen. It's a catalyst process that's taking place. If we have a no fuel misfire, we're saying that our trim numbers will be higher, be a leaner condition than a ignition misfire. Same amount of oxygen. Our no fuel misfire, we're just basically, for that single cylinder, we're just pumping oxygen into the exhaust. There's no extra fuel. And so this process here that I have in blue would not be taking place. So we're not creating voltage at all. And low voltage from an O2 is what kind of signal? Two L's, name association. Lean signal.
Lean.
Computer's reaction is
Rich.
So you see our positive number here, this plus 20% potentially. With the ignition misfire, the blue lines I have here, we'll call that our oxygen, and maybe the black lines, this is fuel now. We got oxygen and fuel coming into this, so we have blue, oxygen, and black fuel. Some of this catalyst that's taking place would maybe be these two guys, right? Oxygen and fuel, and we have the catalyst there to do its job. I don't know if you want to call it burning it or not, but also some of it, which one's fuel? Black. Some of it's going to come across, because not all of it's going to be done externally. We're still going to pull some across that thimble because there's oxygen on the other side too, and we're making a little bit more voltage than we are with the other misfire. And so we're not as lean. Does that make sense? That's the best I can do. I apologize if I still have it off. I think it was absolutely worth doing this, because there are things that I have been teaching wrong for years, and I want to correct them, number one. And number two, the diagnosis is, if we can get this down, this is going to help with some troubleshooting concepts. Another one I was thinking of is EGR. And I've had this wrong forever too. And I used to say this, that when we introduce EGR gas, in fact, I think I have it wrong. It wouldn't be in here, it'd be in section 4. Let's jump there real quick. Can you go there with me for a second? Let's go to section 4.
Yeah, what page?
While we're talking about this, and I want to make a correction. Oxygen sensors and fuel trim, since we're doing this page, it's like one of the last pages in the chapter. I don't want to say that this page is completely wrong. This is section 4, page 20. Section 4. Guys, be careful when you're flipping these pages. You'll tear them if you're too aggressive. All right.
Cover stuff.
What's that? Oh.
Yes. Cover stuff.
All right. So here, let me just describe to you guys what I've said in the past. So this is something else the engine computer will use the oxygen sensor for, is to monitor other systems. And this is true, that the computer will use fuel trim and determine EGR flow. And so I've said this in the past, that if we're introducing oxygen and fuel into a cylinder, and compare that to introducing spent exhaust gas, oxygen, and fuel in a cylinder, what the spent exhaust gas would do is it would displace oxygen and it would cause a mixture to richen. Right? I've said this time and time again, and it's wrong. It's wrong. And it really, that came from this understanding of this tomato sensor and how it actually functions. I guess what I'm thinking about, I don't think I can even draw this, so you're just gonna have to visualize it. If I'm going down, let's say my O2 is doing this. This is how I would always describe this. And we had a short-term fuel trim command that was going a little positive, a little negative. No EGR at all. We're going down the road, driving the car, steady throttle. And we open up the EGR valve. What we would see, and I would describe it like this, is we would see a rich condition. And I would justify that by saying that we're still issuing the same pulse width. We haven't changed the injector, but because we've diluted the mixture, we've taken some of the oxygen out of the cylinder, basically, is what I'm saying. By introducing this EGR gas, we've displaced oxygen. Does that make sense? That would drive the mixture rich. Okay? And so what the computer can do to monitor EGR flow is it can do that very thing. Is it right at that moment, the computer knows it just turned the EGR valve on. What does it want to see off of the O2? It wants to see the O2 go rich. And then the short term will try to counter, and how negative, it's going to start going negative because the O2 is rich. How negative it goes would be the equivalent to EGR flow, and that's what I've said for years and years and years of how this flow monitoring is done. It's just not accurate. I have a case study it's on my premium channel. I have a case study where I have a stuck open EGR valve, and let me back up. For years, I have seen stuck open EGR valves. These cars come in and I'll see negative 25%, that's supposed to be 5, negative 25% fuel trim. Cars barely idling. Now there's some background stuff. You guys just came from emissions, you should know, right? You guys had emissions? Some of you, it's a mixed group. Do we open the EGR valve at idle ever? No. EGR valves never open at idle. So if your EGR valve's open at idle, that car's barely idling at all. Real rough. And I've seen this many times. These cars come in with the EGR stuck open at negative 25%. So my theory of EGR gas, it works. It holds water, right? EGR is going to richen the mixture, and that's how it cools the flame. And you know that's not how it works. But troubleshooting these, it's been fun. I haven't had an issue. I have a lot of different directions I want to go. I'm just trying to emphasize this part here first. So you understand my description here of it being rich would match what I have seen for years, that when EGR valves are stuck open, I see rich conditions. Noted by the negative fuel trim numbers, which is a lean command. Don't get them mixed up. Lean command is because of what?
Rich.
A rich condition. Okay, cool. So everything's nice and, you know, everything flows. And here's what I never realized is we can do this kind of flow monitoring as long as it's a MAP engine and not a mass airflow engine. Without going down that path too far, there's two different ways to measure airflow coming into an engine. One of them would be to measure, this is our manifold, intake manifold. One of them would be to connect a sensor to the manifold. We'll call it a MAP sensor. It's manifold absolute pressure. We measure the pressure in the intake, and the pressure in the intake would be the equivalent of the airflow coming into that engine. You know, how much atmospheric air is coming into the engine, MAP engine. Another one would be where we, you know, throttle plates here, where we put something here that's called a mass airflow. And there are two completely different methods of measuring airflow. You see the mass airflow sensor is external, and we're measuring the air before it comes into the engine, as opposed to a MAP engine where we're measuring the airflow in the manifold. technically speaking, there's two designs. It's called speed density, which is our map, and mass airflow. But for argument purpose, we'll just call it map and mass airflow. Now hear me out. This is kind of more research with the tomatoes kind of brought this about. A stuck open EGR causes a rich condition on a map engine because the EGR valve is pumping exhaust gas into the manifold at least atmospheric pressure. You follow? If we're at idle, there's not much back pressure in the exhaust, so it's at least atmospheric pressure that's going into the manifold, if not higher. What do we do to manifold pressure? If the engine's idling and we have 20 inches of vacuum, absence of pressure, and you open up this big gaping hole, I know it's exhaust gas, but it's still, in a sense, a big vacuum pressure leak. We open up this big giant hole. What does pressure do in the manifold?
Goes down.
Vacuum goes down.
Okay.
That's right. So
pressure
that's
goes up.
yes. Pressure goes up, vacuum comes down. Now the map sensor works just like that. It senses a pressure change and tells the computer, we got extra air, so give me some fuel. So with this taking place, the map is telling the computer that we have a load. What does the computer do in response to a load? Is it adds fuel. Should it be adding that fuel?
No.
Car's still idling, throttle plate's closed. No, it should not be. So why does a stuck open EGR make the mixture go rich on a map engine? It's not because the EGR gas is diluting the oxygen and making it go rich. It's because the map sensor is sensing the load. We have low vacuum, and that's where the rich condition's coming from. On a mass airflow engine, we have the same condition, and this kind of proves it again that this whole fuel sensor, oxygen sensor thing. We do the same thing to a mass airflow engine. This is not here, guys. Do we sense this additional load from the mass airflow, which is out here? You would all agree we have a pressure increase in the manifold or a vacuum decrease, but does the mass airflow see it? No, it doesn't. And if the mass airflow doesn't see it, then we're not getting an extra load signal, so we're not getting the extra fuel. So guess what a stuck open EGR looks like on a mass airflow engine? It looks like a vacuum leak. You'll see positive, I don't remember on my video, it was like positive 10. So you with me on see, I don't know if that's totally related to the tomato and how it operates. I think it could be. It is. The debate with oxygen levels and how that's where it came from, right? We're displacing oxygen. That should make it go rich, and I don't know. I'm not doing well in putting these two together right now in my head as far as the tomato and how it actually works. But do you guys understand where this research has recently taken me? And I have a video on a vehicle. It's a mass airflow with a stuck open EGR that has positive fuel trim numbers, and forever I've always thought they were negative. So how do we justify that? Somewhere down that line is this tomato conversation again. I guess that's the point of me going over this with you right now. Is it worth doing? Was it worth talking about? Is it going to help us in the future? Can we do flow monitoring using the O2? Yes, but this was done on Chryslers. Chrysler did it. These were map engines. So it was more pressure changes in the manifold than it was the dilution of the mixture. This is all good. This all works. GM did it too on their early TBI systems. They did EGR flow monitoring using fuel trim numbers. But it wasn't because of the dilution of exhaust gas, it was because of pressure changes in the manifold. So I just maybe clarify that. So a note here would be everything here is good, but this would be EGR flow testing using the O2 on a map engine would be maybe the correction I'd want you guys to put. Map engine only. Map engine. What's the name I said? See if you remember it. Map engine only. It is called a
Speed density.
speed density. A speed density engine. So EGR commanded on. This is all good. EGR commanded off. This is what happens. Short-term trim is going to drop. Short-term trim is going to increase. But it's not because of the EGR flow. It's because of manifold pressure changes. So I don't know why they just didn't use the map sensor to do it. I don't know. There's still some issues in my mind with all of this, but I'm just kind of doing the best I can with it. Rich lean, O2s. Okay. Fuel trim. Short term does what? What's the number one job of the short term fuel trim? It's going to go a little positive, little negative, from 0% to make the O2 move like this. What do I mean? Where is, let's talk about that 0% number for a second. Fuel map. Fuel map is where the engineer figures out how the engine breathes and matches the fuel to go with it. Lots of variables there, guys. Lots of variables. Altitude, air temperature, engine temperature, volumetric efficiency of the engine. Is it naturally aspirated? Is it turbo? Intake design, cam design, exhaust design, just to name some of them. And then, of course, there's the parameters of the engine. Are we running at idle? Are we running at higher RPM? Are we under load? Are we not under load? So we write this map. It actually looks like a mountain range. If you've ever seen a 3D picture of a mountain range, that's what fuel maps look like. So what is this 0%? 0% would be, it's an advantage to us because I don't need to know the map. For example, maybe on a trying to think of an engine comparison. Maybe on a 2.8 GM, I'm thinking of early model GMs, my injector on time on this car might be 2 milliseconds at idle, and who else made a similar engine close to a 2.8?
Chrysler made it 2.7.
Yeah, we could do that. Let's say 2.7 Chrysler. That's supposed to say Chrysler.
Just put Dodge, it's easier.
We might be at 1 millisecond.
It is.
And let's say for this argument that, excuse me, that both engines are using the same fuel injector. They don't, but this 2.8 GM is getting twice as much fuel as this 2.7 Chrysler. Where was I going with that? I have no idea. I had a thought on this fuel map and I lost it.
3D mountain.
I got it. You can't know, here's my point. You can't know what normal injector pulse width is because every car is different. Some people ask me this, why don't you use injector pulse width in your troubleshoot? And my answer is, I work on 40 different car lines. And I can't know what normal pulse width is because of system designs. And here's what I was getting at. On this design, this system will actually fire all the injectors together one time per crank rotation. And on this design, we're actually firing them in sequential order. So it may take, when I fire this one, it may take twice as much fuel. Now think about this. If we fire all the cylinders once, you're just going to have to agree with me whether you follow or not. Listen, I'm going to talk fast for this part because it's not that important. If I fire all the cylinders, if it's a V6 and I fire all the injectors one time per crank rotation, that means that every time that intake valve opens, that injector actually fired twice before that intake valve opens. 720 to complete the full rotation. So if that thing, I got this backwards. This one's 2 milliseconds. This one's 1 millisecond for my analogy. Sorry.
So that was once.
If I'm firing that 2.8 GM one time per crank rotation, that means I'm firing that injector twice for this to have the right amount of fuel. So I'm only going to fire the injector 1 millisecond, which by the time we're done is 2 milliseconds if you followed me. So in other words, it really got 2 millisecond shots of fuel, but it was double shot as opposed to this Chrysler that was a single. So what I'm trying to compare, here's the point. If you didn't follow that, don't worry about it. Here's what I'm trying to say. You can't look at injector pulse width and know if the car is running rich or lean unless you know the car line you're working on. I work on 40 different car lines. I can't know that. And then they change the design of the injectors and whatever. So here's what I can know. If I'm at 0% fuel trim, this would be 0% fuel trim. This would be 0% fuel trim. I don't care about the map. I don't care about the pulse width. I care about the fuel trim number. If that's at 0, I know it's normal. Make sense? All right. So our 0% is no alterations from the map. I don't care about the map. I'm not doing mapping. Some guys get into that. That's great. You need to learn about what it is before you start doing it. This is aftermarket stuff that you get into fuel mapping and things like that.
Oh, tuning.
Tuning? Correct. So what are we doing here? This would be 0% correction. This would be positive. This would be negative. What does positive do? Positive fuel trim numbers do what? It's rich. That's right. I would say it's adding fuel, right? In positive numbers is a rich command. We're adding fuel. And negative numbers is what?
Lean.
Lean, and we're subtracting fuel. This is what we're doing. From what? What's 0%? The factory preset. So let's say this. Let's use this 1 millisecond. I always draw a block here just to give you an idea. We'll just do a shortened version. This would be engine load, and this is RPM, and then we got these intersecting, areas, right? If we're at a higher RPM, maybe we're here and here, and so we're going to operate in this fuel cell, and down here, if here and here, this would be like my idle cell. Okay, so just talk about this idle block for a second, and this 1 millisecond. What did I need to do to achieve that? Is I needed to know how much fuel pressure we're running. I need to know the size of my injectors. I need to know how long it takes for the injector to open mechanically. I need to know air temperature, altitude, volumetric efficiency, all that stuff, right, to get me at this 1 millisecond. And then that 1 millisecond would be no corrections, and here and here, this would be 0%. And then I'm going to trim it from there. Fuel trim is taking the map and trimming the map. Okay? It's not, see, a lot of guys get the fuel map confused with fuel trim, and they're completely separate. Let me back up. Open loop, closed loop. What's the difference? Closed loop, I trim the map. Open loop, I don't. All the same stuff is occurring. I need to know all these calculations, all my critical sensors. In open loop, I'm not using the oxygen sensor. That's it. Closed loop, I am. And I'm not in closed loop all the time. Wide open throttle, we don't want to trim the mixture. We want to make power, right? Power is 12 to 1, 12.5 to 1 ratios. We're way richer than stoichiometric. Why would we trim that? We're not. Decel events, we shut the injectors off. I don't want to be a stoichiometric during decel. I'm just dumping fuel down the exhaust. Why would we do that? So there's times we drop in and out of closed loop. Closed loop's what we're talking about though when we're doing fuel trim, okay? Idle is where we're at, 0%. So we may see +3, -3, somewhere in that range, around 5% swing roughly. We'll see on that fuel trim number moving up and down. As it's going high, it's a rich command, and that computer's going to add fuel. The result is the O2 goes rich. As it takes fuel away, the result is going to be decreased pulse width. O2 will drop lean. The short term is driving the O2. Number one job of the short term is to make the O2 move back and forth across stoic. This is what it is driven to do. So let's make a vacuum leak. See what happens. Right? Take this same thing and we just pulled a big vacuum hose off. What happens? My short-term fuel trim was kind of happy there for a little bit. We were at 0% and we're going a little positive, a little negative. What do you think happens now? Again, number one job in the short term is to do what to this O2? Make it move back and forth across that switch point. Are we at that switch point right now?
No.
Our switch point is this 450. It's known as a set point. Call it the switch point, whatever you want to call it. We're below it, right? So what's the computer start doing immediately? Adding fuel. It starts adding fuel, and that looks like this. On our short term, this number will start to count up. And how high it counts up will depend on when this O2 reacts and comes back across that set point. How bad of a vacuum leak, right? Depends. Let's in this example, let's use 20%. And now this O2 is back up here. Now what happens?
Take away.
It'll start doing this again. And believe it or not, everything's cool. Depends on how bad of a leak. There's other variables. We start to misfire and stuff like that. But let's leave that out of it. So we're not at 0 anymore, are we? Where are we? We're at 20%. 20% is my new 0. And it will add and subtract from there. I'm going to put plus minus, but is it really a minus? It's really not a negative anymore, is it? No. So it's really, let's just put a range. Let's go 23 and 17. It's not minus 17, but can you understand that 17 positive is technically taking fuel away? Don't get hung up on that. But everything's cool again. I mean, everything's not cool because we have a vacuum leak, but do you understand that we're adding 20% more fuel than what we need it to be? Do you understand that your gas mileage dropped? But your emissions are still good, aren't they? Because what did we do with this ratio? We brought it back to stoic, and that's what it's all about. Now, our OBD systems are designed for pollutant controls. It's not about saving gas, it's about pollutant controls. We don't want to have horrible amounts of gases coming out of the tailpipe at the sacrifice of fuel economy. It's not fuel economy, it's emissions. It's number one, most important. All right. So this isn't maintained in memory, short term. It's not maintained in memory. It's short-term memory, right? It's not maintained. You shut the car off. Where does short term go back to? 0. There's no memory for short term. It'll start at 0. Technically speaking, you start a car, you may see 40% on a short-term fuel trim number, but you're not in closed loop and it's an irrelevant number, and I never look at short-term when the engine's cold and start up anyway, so whoever does that, to each his own. 0 is where it starts. So we have an issue here, and that's going to be when this car starts back up, we still have our lean condition. Once that O2 becomes active, something something very important I forgot to add. This O2 doesn't do that catalyst process until it's hot. I can't believe I forgot that. It's just like a cat. A cat doesn't do its job unless it's hot, right? This O2, minimum 600 degrees, guys. Before that O2 will light off and start doing this process of oxidizing or catalyzing this fuel, it's got to be at least 600 degrees to work. I say that because my next startup, once the O2 heats up and starts to produce a signal, we'll be back lean again, is what I'm saying, without this other memory I'm going to teach you about, which is the long term. So, can you do me a favor or not? Yeah, because that'll pick up and it'll annoy. When I'm editing this later, I'll be like, who's clicking their damn pen? Sorry. He was clicking his earlier too, so. He's crunching chips and eating lollipops, and no, it's fine. Long-term fuel trim. Number one job is to do what? What do I have it listed as in my book? Number one job of the long-term fuel trim is to do what? Test question. That's your third one now. 5 minutes, and I'll let you break for lunch. All right, so number one job in the long term is keep the short term at 0. Is the short term at 0 right now? Nope. No. Short term's at what? 20. Let's give this, in my hypothetical, let's give this long term. This is long term. Let's give this car 20% for each as a limit. So 20 positive, negative 20. There are limits to fuel trim. The reason we put limits on fuel trim is we cannot have a bad O2 sensor report a lean condition and the computer add so much fuel that we have raw fuel running out of the tailpipe and have a dangerous situation. We limit fuel trim. We don't give it ultimate control. So in my example, we'll use 20% as my limit. Well, maybe 25. We'll go 25 just to curb any. Well, wait, you said 23 over here. Okay, all right. My examples aren't perfect. So 25 is our limit, and the computer won't add any more. So you guys understand my short term's like way up here? Do you understand in my scenario that we're almost out of control now with this short term?
Because it's 20.
What's that?
Because it's at 20.
Because it's at 20, correct. And so once we get to that 25, we're not getting any more. That's it. That's all you're getting. So one of the reasons that number one job of the long term is keep the short term at 0 is to give that short term as much control as possible. Because that's the one that's driven to move that O2. Let's give the short term as much control as we can. And if I can bring this number back down to 0, then I have a whole lot more room that short term can still correct for other issues. That's one reason. The second one is to maintain it in memory. So what will happen as soon as this number starts to climb, and every car is different in when this reaction takes place. Some cars it happens right away, other cars you have to drive it for a period of time. But what will happen is the long term will start to add fuel because it wants the short term to come back down to 0. So this one will count up, and as this one counts up, this one will start to count down. And what will happen is the 20 will end up here and the 0 will end up here. And on my map, my 20 will be over here on the long term, and let's use a different color so you guys are following. My short term is back at 0, my long term's at 20. So this guy's 20, this guy's at 0, and now moving up and down. And that's what you'll have. You shut the car off and restart the car, guess what? You have a memory of where you were, which is 20%. And it will start with that number. Can we have an O2 affect the startup indirectly of a car? Even though an O2 is not hot, not active, we're not closed loop, we're not using it, could we have an O2? I have seen it. It isn't common. I have seen startup issues from a fuel trim memory number on a Dodge with a bad O2 sensor. It was a Dodge truck. It can indirectly affect that. It's lunchtime, but I want to fix this vacuum leak first. So watch. Where are we at? I'll give you guys some extra time. Don't worry about it. We are at 20 here and 0 here, and we didn't wipe out the memory. We fixed the vacuum leak. The next thing that happens is we're here, right? Before we fix the vacuum leak, so this continuation down here, you follow? So we got an O2 that's doing this, and right here we fix the vacuum leak. What do you think happens to that O2 signal? I didn't wipe out the memory. We're operating off of a 20% additional correction curve. And meaning we're adding 20% to the fuel curve at that block. I fixed the additional air leak. I fixed the vacuum leak. What, AJ?
Take away fuel.
It will be, but what's the O2 look like is my question. Before the computer starts taking away fuel, you're right, your head's on the right track. That O2 is going to look like this. The moment I plug that vacuum line back in, that O2 is going to look like that. What does the computer look at first? It's another test question. It's on my book. What does the computer look at first to know where to start the ratio? Which one?
PCM.
Yeah, which one's what's the PCM, Ricky, looking at? What's the computer looking at to know, long-term or short-term, to know where to start? Think about your long-term memory. You're a kid and you burn your hand on a stove. Your long-term memory reminds you, if I touch that, I'm going to get hurt. It's going to burn, right? Long-term is what we refer to first. Before we make any decisions in life, it's our long-term memory that guides us. Was that fun last time I did that or not? Was that stupid last time I did that or not? My long-term memory is what I'm thinking about first before I do anything. Right? Should be. Does that make sense? The O2 would go rich here? What's the fuel curve operating on under? 20% more fuel. Right? So I just took the air away, the problem away, So we have an issue. It's too rich. So what's the first thing that happens? What's the next thing that happens? Think about the names I'm giving you with the number one job of the short term, number one job of the long term. Number one job of the short term is to do what?
Stoichiometric.
Stoic. Are we at stoic right now?
No.
Are we above stoic? We are above it. We're adding too much fuel. So immediately, here's what you're going to see, guys. This is an ASE L1 test question. You're going to see that take place. And they ask you this very question and they say, what's wrong with the car? Nothing's wrong with the car. It's fixed. You're watching memory that's about to balance itself out. So here's what happens. Short term's going, we're at 0. Short term was happy before, we're not anymore. Short term starts to go negative because we need to pull this O2 down, right? We hit negative 20, finally we go down, and it isn't always this perfect, but it's a good analogy. There's your set point. And so we're now at negative 20 to get this O2 to move, but is the long term happy with the short term being at negative 20? No, number one job of the long term is to do what? Bring the short term back to 0. So what will happen is this guy will start to go minus, and as this guy goes minus, this guy will come back plus, and then what we'll end up with is 0 and 0. So what you need to do when you look at fuel trim numbers is have all of that in perspective. Which one do you want to look at? You're smiling. That's a good thing, maybe, right? Maybe follow that a little bit, maybe. Smiling's good. Smiling's better than... What's your thought, Ricky? Was that kind of like not a good smile, or is that a good smile?
It's kind of both, but...
Okay, I'll take kind of both. There's something sticking in there. Listen, here's what you want to look at. I'll let you guys break. We're not done with this. When you pull a car in, you want to look at your long-term fuel trim number primarily. Look at your long-term. That'll tell you how the car's been running. When we come back from lunch, I want you guys to give you where we're going. When we come back from lunch, all I've described to you was one cell. You need to understand that there are learned memory numbers all the way up this area. And we don't just look at fuel trim numbers at idle. We also look at them at higher RPMs that give us a guide into how that engine's running. Okay, we'll cover that part after lunch.